Hello everyone. I will be talking about my capstone project for the Master of Quantum Science and Technology program at UCLA. The project was undertaken by me through the mentorship of Professor Bahram Jalali in the Electrical Engineering Department. The title of my project is Neural Network Schrödinger Equation Acceleration. The goal of this project is to demonstrate neural network acceleration of the classical nonlinear Schrödinger equation and its implication for the quantum Schrödinger equation. So first, I will talk about the classical formulation and then move on to the quantum formulation. Optical fibers are widely used in telecommunications for transmitting data over long distances with minimal signal loss, enabling high-speed internet, television, and telephone services. They are also employed in medical imaging such as endoscopy and in industrial applications for sensors and lasers. In the field of quantum technology, optical fibers play a crucial role in quantum communication, quantum key distribution, as they can transmit quantum states such as entangled photons over long distances with high precision and low noise, making them essential for secure quantum networks. There exist three methods for simulating optical propagation in dispersive and nonlinear media. The first method is by actually doing physical experiments. Comes along with it the problem of maintaining an adequate signal-to-noise ratio at high information transfer rates in an analog device. The second method is the conventional split-step Fourier method, which is used to perform computations. However, it has a large memory requirement, which may be prone to getting occupied in a short while of running. So recently, quite a few research groups all over the world have come up with the idea of using deep learning for approximating the SSFM. I have also explored this aspect in my capstone project. The nonlinear Schrödinger equation describes pulse propagation in optical fibers. It is one of the canonical equations of physics which can be derived starting right from the Maxwell's equations, followed by a series of assumptions and approximations. The NLSE is an essential tool in optical data communication. It is used to simulate the propagation of pulses in optical fibers. The NLSE is a foundation of new class of computational imaging called Phi-CV, which is invented in the Jalali-Lab. Phi-CV makes use of the nonlinear Schrödinger kernel to incorporate physics into the vision algorithms, thereby reducing errors and improving the accuracy of tasks like object detection, image segmentation, and motion tracking. The NLSE is also used for Bose-Einstein condensates and hydrodynamics. We will see in a few slides how the NLSE maps directly into the quantum time-dependent Schrödinger equation. So our part goal here is to discuss a mapping between the quantum time-dependent Schrödinger equation and the classical nonlinear Schrödinger equation. So let us briefly introduce the latter. The propagation of light in optical fibers is governed by the NLSE or the nonlinear Schrödinger equation. It is a complex equation with coupled dispersion and nonlinearity effects for which no analytical solution exists. The widely adopted approach for solving the NLSE is the split-step Fourier method, although it is a time-consuming iterative process. Interestingly, each step in the split-step Fourier method involves a linear operation of dispersion followed by a nonlinear operation called the nonlinearity or the self-phase modulation, thereby resembling a typical neural network block. In this project, I have explored the design and implementation of a neural network to approximate the solution of the NLSE more efficiently. So here in front of you, you have the NLSE, starting right from the Maxwell's equations, followed by a list of derivations and approximations, gets us to this simple looking equation. We want to solve for the pulse amplitude A, which is a function of position and time. The D and N terms here stand for dispersion and nonlinearity or self-phase modulation. These two terms depend on various material and pulse parameters, and here are the expressions for D and N. As you can see, these are really complex looking expressions. Here, alpha is the fiber loss parameter, beta 2 and beta 3 quantify the dispersion in the fiber. Gamma is the nonlinearity parameter. The operator n hat is also called as the self-phase modulation operator because of the second term here. It depends on the square of the amplitude. Hence, the amplitude itself affects the nonlinearity operator. Also, it is important to note that in literature, the variable A is sometimes interchangeably denoted by E. They both mean the same thing. The exact solution to the NLSE is given by this implicit equation. However, if you recall the Baker-Campbell-Hausdorff formula from matrix theory, it relates the product of exponentials to the exponential of sums of matrices. That results in the approximate iterative solution given by the last equation here. H is the step size in position. Smaller step size h means a better approximation. So using a small step size and having multiple steps is basically what SSFM is. However, it is important to note that as you increase the number of steps in SSFM, the computation time also increases, and we shall discuss this in more detail. So without further ado, here is a block diagram I created for the implementation of the neural network for doing pulse propagation. So you start with creating some training and testing data using the split-step Fourier method. You also generate some ground truth, which is the data created using more than sufficient number of split-step Fourier method iterations, because the ground truth has to be a very accurate result. So you split the training data into inputs and outputs. Here, the inputs are actually the pulses that are coming out of the optical fiber, and the outputs are basically pulses that go into the optical fiber. Our goal here is to perform pulse reconstruction, hence we use these terms in a different manner. Once that is done, we build and train the neural network, which we have termed as the Nonlinear Schrödinger Neural Network, or the NLSNN. Upon training the network, you use it to test the data that you have created in order to generate some testing output. Simultaneously, you also generate some output using the split-step Fourier method, such that both these methods have comparable latency, and then you can finally compare the accuracy of both these methods with each other and with the ground truth. These are some realistic values of SSFM parameters that we use to generate the data. We neglect fiber losses, which is quite a realistic assumption in many cases. We set gamma to 0.0101 in SI units, and beta 2 and beta 3 are set to these values. In order to generate the ground truth, we set the number of split-step Fourier method iterations to about 10,000 to ensure that the ground truth data is quite accurate. On the right, you can see how various other things change as you change the number of SSFM steps. So in the figure on the top, upon increasing the number of SSFM steps, that increases the latency of the solver as expected. And in the figure at the bottom, you can see that as one increases the number of SSFM steps, the relative mean squared error of the solver decreases, which is also what is expected. Because if you have more steps, you expect to generate more accurate data at the cost of latency. So now I will describe briefly the architecture of the NLSNN. The convolution layers act in the standard manner as they do in a generic convolutional neural network. However, the activation layers are physics-inspired. They multiply a complex number of unit magnitude to the convoluted layer, thereby resembling how the nonlinearity acts in the SSFM, if you recall that. So the nonlinearity basically multiplies e to the iota lambda phi, where phi can be calculated as the absolute value squared of the convoluted data, whereas lambda can be set to be trainable or non-trainable. In our model, we set lambda to be trainable. That results in the updated X. Here we discuss some parameter values of the NLSNN. On the right, you can see how various other things change as you change the number of hidden layers. So as the number of hidden layers are increased, that results in an increase in latency because the data has to pass through more number of layers in the neural network, and hence it takes more time. In the figure at the bottom, one can notice that upon increasing the number of hidden layers in the neural network, the relative mean square error initially decreases and then it becomes constant. This indicates that you don't really need a lot of hidden layers in the neural network, and something around 10 should be sufficient. The kernel size we choose for each channel is 55, and we separate the data into real and imaginary components because PyTorch does not yet have a functionality of dealing with complex data directly. The learning rate for each channel is 10 to the minus 4. Here is an example of the input data in the time domain. So on the left, you have super Gaussian pulses, which are given by this function. And on the right, you have a randomly modulated Gaussian pulse. So the super Gaussian pulse is a purely real pulse, and it has no complex phase to it, whereas the randomly modulated Gaussian is a complex pulse, and in this figure, we have just plotted the absolute value of it. So we test both the methods on this data. This table summarizes the results we obtain for the various data points. The first column displays the kind of testing data used. The latency of both methods is fixed and listed in the third column. A comparison of the losses are performed in the second and fourth columns. Notice that for the super Gaussians, the loss using the SSFM comes out to be of the order of 10 to the minus 9, which is much smaller than the loss while using the neural network, which is of the order of 10 to the minus 4. In the case of randomly modulated Gaussian, the tables turn, and the neural network results in a much smaller loss than the split-step Fourier method. This justifies the fact that neural networks are good at learning complex patterns in data. Here we have visualized the reconstructed pulses. On the left is the reconstruction of the randomly modulated Gaussian. The green plot indicates the reconstructed pulse using SSFM, whereas the other two plots indicate the reconstruction using the neural network and the ground truth itself. As you may notice, the neural network does a much better job in the reconstruction compared to the split-step Fourier method in case of the randomly modulated Gaussian. Whereas in the case of super Gaussians, which are purely real, the split-step Fourier method does a better job in reconstructing the pulses. Therefore, we have achieved a new result in the domain of fiber optics. Let us see how we can further make use of it in quantum science. By following a simple procedure, one can obtain a mapping between the classical nonlinear Schrödinger equation and the quantum time-dependent Schrödinger equation. So here in front of you is the nonlinear Schrödinger equation. In this, we set alpha to 0 as before to narrow our work to the no fiber loss case, and then the NLSE equation becomes the following equation. Next, we perform a simple change of variables by replacing the pulse amplitude with wave function variable psi and by interchanging the position and time variables. This results in the equation being rewritten in this form here, where you have a new variable h, or rather a new operator h, and the operator h takes this form given by the second equation. Next, we replace z by minus z and beta 2 by h bar over m to get this modified operator h bar, which now resembles a quantum Hamiltonian. This quantum Hamiltonian has a potential function which is proportional to the negative of the squared of the wave function. So this can be further written in the form of the time-dependent Schrödinger equation, thereby proving the mapping. So the time-dependent Schrödinger equation is given by this equation right here. If you want to perform the evolution of wave functions using the time-dependent Schrödinger equation, we can use this result given by the second equation, provided the Hamiltonian is time and wave function independent. We can use this result instead, which is an integral expression, in the case when the Hamiltonian is time dependent, and tau here is the time ordering operator. But in our case, we have the Hamiltonian to be proportional to the negative of the squared of the wave function. Therefore, it satisfies none of these two cases, and using the neural network could be a good attempt, just like one may use the split-step Fourier method. So we have showed that in the case of optical fibers, the NLSNN works great for a complex pulse in terms of latency and accuracy. For a standard pulse, we use the split-step Fourier method because fewer iterations are required. By performing a simple change of variables, we arrived at the versatility of the classical NLSNN as an accelerated solver of not only the NLSE, but also for the quantum time-dependent Schrödinger equation with a potential proportional to the negative of the square of the wave function. Now you may be thinking, why do we actually need to deal with such a Hamiltonian? So this Hamiltonian appears all the time in Bose-Einstein condensates in the name of the Gross-Petaevsky equation. It also finds applications in plasma physics, fluid dynamics, and condensed matter physics. Its versatility makes the NLSE a fundamental tool for understanding and predicting complex wave behaviors in diverse physical systems. With that, I would like to thank you all for your attention.